we start? Some more
Yeah,
students.
sure.
You can share the screen, that's fine.
Okay,
Okay,
since roughly 42.
51 students are online, yeah.
Okay, 51, okay.
Some more are joining, I think.
Okay, so let me start showing my screen. I think it's clear, I hope.
Yeah, sure.
Okay, so yesterday we discussed rotational spectroscopy. That was basically connecting the whole idea of angular momentum and rotational kinetic energy generated due to rotation of molecule, and then corresponding spectra, which happen in very low energy, literally, roughly in the range of 1 to 10 centimeter dose. Okay, so this is the lowest energy of a system. And I was also, I was intriguing to ask or show you this. Actually, this is one of the spectrum of carbon monoxide molecule taken by a far infrared absorption spectrometer, okay, which is connected to the bolometer. So you can see that here there are some bands that start from here. This band is J is equal to 3 to 4 transition. Okay, which is, I just want to show you like how a rotational spectrum look like. If you take rotation spectrum of water, it will be very broad, literally. You see that you feel like it's forest if you take. It's the same thing for many molecule, but you can pinpoint it here. This is J is equal to 3 to 4 transition. So what mean by J is equal to 3? When you calculate the energy, it will be B into 3 into 3 plus 1, right? J into J plus 1. That's equivalent to 3 into 4, 3 into 4, that's 12B, right? That means 12B is equivalent to this value, which is 15.38 centimeter inverse, right? So if you divide, if you can calculate B is equal to 15.38 divided by 12, this value comes around 1.92 centimeter inverse. This is the rotational constant of carbon monoxide, which is mentioned very specifically here, carbon 12, right? And if I take the last one, this is how you can calculate it very, very precisely. I only took 2 digit, you can calculate it. This is again taken from the IISER spectrometer. You can have very high resolution spectra. Okay, later on, this is how some of the micro spectrometer equipped with very high resolution. So you'll be able to calculate very precisely. Once you know the B, you will be. This is B for I can say rotation transition from 3 to 4, and there is another transition. There are many transitions. This is okay, 4 to 5 and 5 to 6, all the way up to 10 to 9 to 10. You can see this is 9 to 10 transition. So that means a B of 9 will be. There is something I made something wrong here. This is not correct. Sorry, this is 12B, but we have to calculate the difference, right? So that's why I made wrong here. So for fourth transition, it will be B into 4 into 4 plus 1. That will be 20B. The difference between these two is 8B. Okay, so that means 8B is equivalent to 15 point. Otherwise it won't match, right? 15.38 centimeter. That's why I said I made a mistake. So when you calculate B, the B will be 15.38 divided by 8. That comes out to be 1.92 centimeter. Okay. So you remember I was drawing this 0, 2B, 6B. Okay. Again, 6B, 12B, 20B, it goes on, right? So this difference is 8B. That is this band. Okay, so for B equal to 9 to 10 transition, you have to calculate for the B9 state, which is equivalent to 90V. Okay, for B is equal to 10, it will be 110V. So the difference is 20V. So if you do 20V, 20V is equivalent to 38.41 centimeter inverse. So you will be having B is equal to 38.41 divided by 20. This is equivalent to some value approximated as 1.920, etc. So you see that B extracted from this, any of these graphs will give you approximately with the same value. Of course, it may change slightly depending upon the conditions that we call unharmonicity, that this centrifugal distortion constant come into play. You also remember yesterday we discussed how unharmonicity can play a role to bring the centrifugal distortion constant D10 partially, if I am correct. And another thing is very important. This is actually taken from one of our old papers, okay, Gilliam et al., 1950, Journal of Chemical Physics, book given in the reference given in the book of Colin Banwell. Okay, so I can insist you to read the book. Okay, and I am also telling you as your friend, so I am just telling you guys to read this book. It's free download because it's copyright expired after 20 years. You would see them free available in the internet. Okay, so you can just download it. Okay, and then read it, all the chapters. I mean, second chapter is for rotation, third chapter is for vibration, fourth chapter is for Raman, and it goes on. So rotation, Raman, and rotation, vibration, and Raman is very beautifully explained in the book of Banwell. So if you use university guides or something for your studies, I encourage you to read the basic book, which is Banwell. If you are not satisfied with this, I will of course suggest you. Atkins has given Atkins is physical chemistry altogether. Same thing, another one is there, Ira Levin. Okay, these are the books I refer and I normally advise also. Very good books. Ira Levin, physical chemistry. Okay, Levin has many books. Okay. Many books actually, so I'm talking about physical chemistry books. Another one is Peter Bernard, if you are further interested on molecular spectroscopy. So I know that I was actually came through the same situation when I was a BSc student or MSc student. So I used to get some textbook material, just university guides, right? You have to read it and maybe you need to correct it even if you read it. You see some of the things are wrongly written there. Okay, so I encourage you to students to download yourself. You have free access to this book. I can get Ira Levin, Peter Bernard. So Peter Bernard is also free downloadable, and this Banwell and physical chemistry books. Atkins also free download. Most of them are copyright expired books. You will see free download available in the internet. Okay, so coming back to carbon-13, we know that natural abundance of carbon-13 is 1%. You see him coming out here, very clean. Okay, so this is carbon-13 and this is C12. This is 1% if you calculate the population. This is 99%. Okay, so this is how we understand very clearly from rotation spectra for carbon monoxide, and the presence of the isotope can be really picked. And this experiment has done in 1950, almost 71 years before. Okay, so you have to think now still people use it. That means you use it actually as a tactics or as a method for calculating and understanding molecular structure. Okay, so I will move on slowly into something called Jablonski diagram. Jablonski diagram will represent the molecular energy levels. Okay, so when I draw it, you'll see many. If you just type it in Google Scholar or anywhere in Google, you'll see many in the image. If you take, you'll see many diagram, many format has been mentioned. I'm just showing one of them, S0, which is your common ground state, electronic ground state. Then you can have S1. Okay, in the first class I was mentioning there is a transition which happened from here to here, goes up here, right? This is I call as electronic transition. You remember electronic transition. Okay, this transition goes up, which is causing an absorption event that you are seeing any material, it color, right? It absorbs that light and complementary color will be observed by you. Suppose we are given with permanganate, potassium permanganate, it absorbs 540 nanometer wavelength and it shows its complementary color that you see as some violet color or slight pinkish violet color, right? Fine. So this is coming in the range of roughly 2 to 2.5 electron volt. Okay, so I can write this will be like, so I will write this is electronic energy, they comes as roughly 1 to 2 electron volt. Then you have vibration level. So I have common vibration level here. You can write V is equal to 0. Then I have vibration level V is equal to 1. Then V is equal to 2, etc. Okay. Similarly, so now in each of these vibration level V0 to V1, I have rotational states, small energy levels here. Okay, these are called J levels. You can call J double dash or J dash, whatever. These are rotational levels. It goes on like that. So what I am saying here, you remember I was mentioning you V bar or omega. We can discuss whatever it is. It is vibrational frequency. They comes in the range of roughly close to say 0.5 electron volt or smaller. No, not that much. It is milli electron volt. So you can think about something around 300 to 400 or 200 to 400 milli electron volt. So this will be roughly in nanometer will be like you have electronic states coming around 400. So maybe you can think about 250 to 800 nanometer. Many scales. This is in energy, in electron volt, right? And it can be in joule. You can write it in joule. You can write it in wavelength. You can write it in frequency, whichever way you want, in wave numbers or so forth. So these in wave numbers will be roughly around 20,000, 20K to 10K. This will come around some 4K to 1K. Okay, then the last one, the discussed one, is just roughly 1 to 10. This will be in centimeter inverse. So you see now this will be micro electron volt. Okay, so it goes on like that, this discussion. So you see roughly, I mean in this figure will tell you roughly, this I have taken from internet, from ResearchGate, where one of the depositories people normally use. You can see here an S0 to S1 transition. So you can see this is also not very important. This is not scaled. I was saying that this transition is S0 to S1. You are just climbing a staircase, and this is the ground floor, and this is the first floor of your building. Okay, you consider these are the staircase. Okay, the staircase steps, and each staircase step has again energy levels 1, 2, 3, 4, etc. So these are exactly rotational states. These are vibrational states, and these, the long ones, are rotational electronic states. And even in the electronic state, you can have S1, S2. They are called singlet states, and you can also have triplet state depending upon the electron pairing. So this is how the entire system look like. So we discussed this small guy, rotational level. Now we will discuss about this guy, vibrational level, this transition. That is a transition from 0 to 1 or 0 to 2 or 1 to 2 and so forth. Okay, so that's where infrared spectroscopy comes in. Okay. So I will take straight away why it is coming from. It is due to oscillation of dipole. We in the last class of the second lecture, we were discussing about a bond length, which is actually a rigid unit in the beginning, and then we say non-rigid rotor, this bond length is elastic. Why it is called elastic? It moves. So I have a ball, okay, connected by a spring to another ball, A and B. Now, this A and B, which can move each other, this create a kind of energy distribution, and that is why it is originate. This oscillate. This create energy distribution, and this will cause a vibrational event to occur. Okay, so that is how it is, and then now I can simply think about the whole idea of carbon bond. I was mentioning 1.54 angstrom, roll half 1 story, and I was exaggerating it is from 1.3 to 1.7, but in reality it is, I was just exaggerating. It still can vary from 1.53 to 1.55. Okay, this is actually a clarification from yesterday class. It cannot move too far. I was thinking about it afterwards to tell you very clearly. So now this bond, it can have some fraction again. It can be again 3, 5, or 3, 2, whatever. So it is a digit, right? It moves. That you see that now a histogram. I just want to bring you that attention. So now here to explain this. So I was saying that here, what I mean to say here was that a bond is always moving or say vibrating each other. That will give you different R value. And your V will goes as 1 by R square. You know that, and now you already know that it's 1 by R equilibrium square. That is the relation that we discussed yesterday. Now, let us take hydrogen chloride. This is a simple example in which a small atom connected to a big atom, right? 1 to 35, right? So that's how the difference is. So it's a small atom connected to a big atom. Now when I place it in terms of energy, okay, in place in terms of energy, your hydrogen is here, your chlorine is on the y-axis locked, okay, big atom. I am sitting on top of the chlorine, okay, and now this is connected to hydrogen through a bond. Okay, so I am sitting at chlorine and looking at what happened to hydrogen. So hydrogen can move from here to here. Now assume that chlorine is not moving, and then it can take either this position or this position, H double dash. Okay, so what happens that if you give some energy to this particular bond, okay, what will happen is that the energy of the overall energy, vibration energy of the system goes up here. So what happened? The hydrogen atom comes here. Okay, this is H, and they get separated like this. Okay, so this will have an energy you can call E2, and this will have an energy E1. E1 will be greater than E2. Then still I am the observer sitting here observing it, right? So you can see that when I go up, what literally happens is that the vibration, the oscillation strength increases. I will try to vibrate more faster, right? That results in an energy increase. So what you are doing is literally dumping energy over here so that the hydrogen will try to vibrate more, some thermal energy. You just, what practically you can do is just heat it, right? You give multiple of kBT, where K is a Boltzmann constant. If the temperature increases, you will populate, give more and more thermal energy, so then it won't try to vibrate very fast. This will result in something called a kind of a parabola. Okay, I'm not drawing it properly, but it's a parabola. Okay. It's a parabola shape. Now I can connect this. Now I say that its bound is like a spring. It's like a spring. The spring stretches and compresses very clearly. That creates this event. I hope that is clear. That will have couple of things. I can calculate it restoring forces. If you study that, you have studied maybe in your higher secondary something called Hooke's law. I remember I have done this when I was in higher secondary school, some class of physics practical, to find the force constant of a spring, right? This is Hooke's law. Hooke's law, using Hooke's law, F is equal to K minus K into R minus R equilibrium. F where K is force constant, right? So the corresponding energy classically I can write it as half K R minus R equilibrium all square. Okay, this concept is called simple harmonic oscillator model. So the assumption was I am fixing chlorine on the wall and I'm just clamping by bumping energy into it, right? I give more energy, it goes here, then it goes here, it goes here. Now I have to assume that in simple harmonic oscillator model, I will have fixed. So what will happen? The energy is fixed. I will, of course, vibration energy is fixed, right? This is an oscillation. It will have a gain quantization. So classically, I can write the energy or observed energy equivalent to 1 by 2 pi, okay, into under root of k by mu. This we have partially touched up in the yesterday class, where k is the force constant, mu is the reduced mass. Force constant. You remember I can write him as in terms of wave number. This is in terms of frequency. I type wave numbers. I just need to add C here, 2 pi C, right? Correct me if I'm wrong. This will be k by mu in centimeter inverse. This will be otherwise in hertz, right? This is in frequency. Which concept I am. Now this is in centimeter inverse. I introduce speed of light versus speed of light. That's how you convert, right? Okay, so vibrational energy is quantized. Vibrational energy is quantized as we discussed in the case of J. In the case of J, right, we have values J is equal to 1, 2, 3, etc. Here we have also same possibilities 0, 1, 2, 3, etc. Okay, so this is called vibrational quantum number and this is called rotational quantum number. You will study this when you come to quantum mechanics course. Okay, you will come to this very clearly when you come across the quantum mechanics course in the third semester, fifth semester as your sir suggested. Great. So what is the corresponding energy? I can write it energy as E of V, which is equivalent to V plus half into H. So you can write it in many ways. I can write in terms of, this is in joules. This will be in terms of low number, observed value, which will be in centimeter inverse. So we can occupy many values. If V is equal to 0, your EJ or E0 will be equivalent to half omega bar oscillation. Okay, right? This is called 0 point energy. Okay, so if you want to see the absolute energy, you have to introduce a value of H in there. Okay, this H will come in. So absolute energy is 0 will be half H nu, right? So half H nu is actually your absolute energy, your 0 point energy. That means even at absolute zero of temperature, a vibration event is occurring. Keep in mind. This is normally the question that you would expect in a class. I was asking when J is equal to 0, your B will go immediately 0. Whereas in vibration, your V is equal to 0, that means that you will still have some value. I think I was mentioning, I will show you that in the next slide. That means, very simply, you think about your parabola like this. But sorry, my axis is been, I have to change it. This is your R equilibrium. You remember I was defining R equilibrium, and V is equal to 0. This is half H nu. Okay, V is equal to 1. It will be 3 by 2 H nu. V is equal to 2. It goes 5 by 2 H nu. Goes on. This difference will be H nu. Okay, so that's how it is. And so it is very clear that you still have an energy left even at lowest energy level V is equal to 0 situation. This is coming from Heisenberg uncertainty principle. You cannot have both energy and position defined at the same time. It goes as h by 2 pi. Okay, so that I will leave you for discussion where we discussed about the Planck constant h. Okay, I request you to recollect it. Again, unharmonicity. So I said now, this was for harmonic oscillator where you consider an equation y is equal to x square kind of a type, right? Is y here f is equal to, we started with, right? F is E is equal to k x square, where x is equal to r minus r equilibrium. Okay, it comes out to be like this. Now you have something called unharmonicity. Why unharmonicity comes? I consider compound, a molecular bond, as more complicated as if I get more vibrational energy. Now an atom is connected by another atom by a spring. If I get more vibrational energy, my bond length will change, and the bond length will change if I get more and more vibrational quantum number. Completely different from my previous state. That means I have to follow some specific relation. So I can get a lot of vibrational energies in terms of KBTs. I was still mentioning because KBT comes from Maxwell distribution, right? If I get many of that, I will get into very high vibrational quantum number and my bond break. HCl will break into H plus and Cl minus, simply heating it, right? At high temperature, become ions. It is possible, right? It is, you know that. So what happens here is that something like this will come up. Your energy axis now will have a new defined energy. Instead of a parabola, you will end it if you plot. This is energy. This is internuclear distance. So this can be in kilojoule per mole or whatever you think versus in nanometer or angstrom, whatever. Okay. So what happens is that original parabola now deformed into something like this. Okay. This is something you might have seen it, that your V is equal to 0 will be here. Your V is equal to 1 will be here. This will be V is equal to 2. You can call 2. 3 comes here. 4 comes here. 5 comes here. 6 comes here. 7, 8, 9 keeps continuing. It's become continuum. So you see here, this is where you defined as your D equal. This is called dissociation energy or D equilibrium, and a distance from here to here is called D0, from 0 point energy to the D equilibrium. This is how it is very clearly defined. So you can have transition possible. So previously for an unharmonic state, sorry, for a harmonic oscillator, you can have only possibility of delta V is equal to plus or minus 1. Okay, this is the selection rule for a harmonic well. Whereas for an unharmonic well, you have selection rule in which delta V is equal to plus or minus 1, plus or minus 2, plus or minus 3, etc. That means I can have transition from here to here, here to here, here to here, because it is an harmonic. In this population strength and all will differ. I don't go into those details. What is more important, that this will give you omega, I is mentioning omega bar observed. The second one will be 2 omega bar observed and 3 omega bar observed and so forth. So now if it is anharmonic, this will not be exactly same, it may be very close by. So you got it. Why? Because they are, the difference between V1 to V2 will not be equal as V0 to V1 because of the unharmonicity. A very big scientist, his name is P.M. Morse. Okay, he gave a beautiful empirical relation. It's called Morse potential curve. He defined E as d equilibrium into 1 minus exponential of A into R equilibrium minus R all square. Okay, this has come out of the square. I will check whether it is outside the box or inside the box. Okay, I think it is. Okay, so that we have to see. Okay. These two either here or here. Just cross check it. So this relation containing d equilibrium, you already know that your d equilibrium, which is the dissociation energy, A is a constant, all other things we know, R equilibrium and R, which is unharmonicity constant. Okay, so unharmonicity constant came out very beautifully. So now this value changes with respect to the value of the unharmonicity constant. So I can write, I am not going to derive it, instead I am writing 0 to 1 transition will have energy defined as omega E, which is the equilibrium energy, into 1 minus 2 Xe, where Xe is the unharmonicity factor, A or Xe you can call it. For 0 to 2, it will be 2 omega E into 1 minus, okay, 3Xe. It goes on. So I can have 0 to, so this is 0 to 1, we'll have this energy. This is called the fundamental vibration. Okay, this is called fundamental vibration. This is called overtone, first overtone. You can have second overtone. So normally first overtone itself, you see how the population distribution look like. Some molecules show first overtone. So I was mentioning V is equal to 0 to 1, V is equal to 0 to 2. That means you have possibility of transitioning from 0 to 1 and 0 to 2, right? There the maximum population is. You can also have some population here as well, according to Maxwell distribution. You remember I was discussing Maxwell distribution. I can write n when V is equal to 1 to n V is equal to 0. This distribution goes as exponential of, you remember that expression, right? H nu or H nu divided by kBT. So for if your omega bar, okay, so if it comes omega bar, then it will be like this. C into omega bar. So this omega bar is equal to say 1000 centimeter inverse. Okay, 1000 centimeter inverse where normally vibration appears. Then you calculate this distribution as you can put it value of H is 6.626 into 10 power minus 34. KBT is 1.34 into 10 power minus 23, and T temperature is 300. If T is 300 Kelvin, so I can get this value as roughly 0.08. Okay, this is what I get. No, 0.008. That is equivalent to only 0.01 percentage. Sorry, 0.1 percentage. So it's a fraction, so I can convert into say now as 0.08, which is approximated as 1 percentage. That means at V is equal to 1 level of this vibrational ladder, you will get only 1% of the population. I hope that it is clear to you. Whereas 99% of the population sit over here. Okay, this is how an harmonic oscillator will look like, and then you see that then the possibility of V is equal to 1 to 2 transition, you will see very less in a vibration spectrometer, because that proper population in V1 is very less, so the transition probability will be very less. I hope that it is very clear to you. Now, I will have to mix now this idea of anharmonicity when rotation get coupled to vibration. There, I hope you studied, maybe in your higher class you will consider, I can write E total as E vibration plus E rotation. I am skipping electronic and translation. I am only considering this. This is something called Born-Oppenheimer approximation. So Born-Oppenheimer approximation suggests that if the vibration energy is 3 orders higher than rotation, I can just avoid their interaction. Okay, so that means rotational time scale I was mentioning, it is happening in nanosecond or maybe very slow, whereas vibrational event happens in nanosecond to picosecond rotation, right? I was saying nanosecond is 10 power minus 9 second, okay, or that range, whereas vibration happened 10 power minus 13 second. Electronic absorption happened 10 power minus 16 to minus 17 second. So minus, okay, that's very important. That means close to 10 to 100 attosecond. This is very important. This is electronic. This is vibration. This is rotation. I'm mentioning by their corresponding notation so that it is very clear to you. I think it is very thorough to you. That is why Born-Oppenheimer did. I separate them because one event has actually at least different in time scale. So I assume that I approximate that they don't interact. That's how Born-Oppenheimer approximation came. And then he calculated separately the energy of both of them. Yesterday we mentioned, I remember we have calculated the E of J of an anharmonic rotor as V into J plus 1 minus T into J square into J plus 1 all square, right? It goes on. Other terms I normally avoid. Then for delta V is equivalent to, just now we have calculated V plus half omega E. I also skipped some of the part, but it include another term XC into V plus half. It's again, I only consider up to the cubic terms, square term, so that we don't consider other ones because they are normally negligible. You can have cubic and quadratic terms comes afterwards. I just skip them. So if you mix both of them, you will have a mixed equation which containing these particular forms. And I can have a defined energy level I was just mentioning. very nicely here. I how to draw it. It's a very complicated to draw. So I just make now two axes. J is equal to 0, V is equal to 0, to situation. Okay, here I call, maybe I have to discriminate between V0 and V1, so I am calling this as double dash. This is what actually given in the textbook. You please see it. Okay, you please see it. What's the time? Yeah, 4:10. Okay, great. So what happened? You have rotation state, J is equal to 1, 2. Okay, this is schematic. Sometimes I do exaggerate drawing, so you don't worry about it. Okay, just to show this argument. Now I have the situation here. V is equal to 1. Here I call J dash is equal to 0. J dash is equal to 1, 2, 3, 4, etc. So when a vibration occurs, I was telling you that, when a rotation occurs, there was roughly 10 power 3 times or 10 power 4 times vibration occurs. Right? The vibration is so fast. So you can have literally a transition which can be from J, delta J equal to plus or minus, and delta V is equal to plus or minus 1. So what are the possibilities? We can have plenty of possibilities, right? You can start from here when I have to say V is equal to 0 to 1. It will be going up here all the way up to here. Then I can have here to here. Correct me, right? If I am wrong, it goes here, goes here. So many transitions you will see. This is the ground state V0 to V1, excited state, vibrationally excited state V1. So you will see in a spectrum very clearly this. Okay. So in the second case, what happens? That is coming from, this is, I can have a probability minus 1, right? It's starting from 1 to 0. Okay. Shorter energy. Up. Something wrong. 1 to 0. Again, this is not correct. This is from 2 to 1. This is from 3 to 2, and so forth. Okay, 4 to 4. 4 to 5. 3 to, then 4 to 3. Correct. So this will become, you can have here two situations, delta J is equal to plus 1 for all these, and delta J is equal to minus 1. Delta J is equal to 0 is not shown. This will end up in having, distribution of energies in which a vibration envelope shows bands. Okay, you can have your original band somewhere here. Okay, I have to mention that properly, otherwise you get confused. This is your omega 0. You get actually energy on the either side. These are called R0, R1, R2, etc. This will be P1. Okay, there is a reason to mention it. I don't explain that. P1, P2, P3, etc. You get different energy levels. So on top of the vibration, you see rotational state coming out. This is how, with respect to vibration. I think I should skip it. I will show you this part because I don't have much time. I encourage you to read it. So you see a beautiful spectrum of carbon monoxide given here. This is a rotational vibrational spectrum of carbon monoxide. The same thing I was mentioning, the R branches, R0, R1, R2, R3, etc. coming out, as well as the P1, P2, P3, etc. coming out. This is due to rotation coupled to vibration. Okay, clearly. And this is actually the fundamental transition of carbon dioxide. Anyway, you may be familiar with this other rule, we call this is asymmetric stress, and this is carbon monoxide, right? Because carbon monoxide, it's a heteronuclear atom. It shows up a band at 2143.28 exactly. This is in detail given discussed, and this is your 0 point where omega 0 comes in. Omega 0 is omega E minus 1 into 1 minus 2xe and so forth. Okay, everything has a bar. It's in okay, fine. Then you can get it. This you will be measuring in a spectrometer. You see carbon dioxide, how does it look like? P and R branches. P is from delta J is equal to -1. Here delta J is equal to +1. For delta V is equal to +1 transition. Hope you understood this, and it is clear to you very well. So this is again fundamental stretching band of carbon dioxide. Carbon dioxide, you know the molecule C double bond O. It's a 3 atoms, so you have 3 atoms. So if I have n is equal to 3, then you have, you understand, right? This is a free, you know how many degrees of freedom they have. 3 atom will have 3 into 3 degrees of freedom. 1 atom will have x and y and z, right? We already said that it's a 3-dimensional system. I can define a Cartesian coordinate as x, y, and z. So I have 3 possibilities to fix it. So I'm fixing on the Cartesian coordinate 1 atom, then the second one, and the third one, then together form a molecule. Now I have 3 into 3, 9 degrees of freedom. Okay, out of that 3 will be translational. Okay, and 3 will be rotational. So I will have 3n minus 6. Okay, for carbon dioxide it is 5 because rotation on one axis is arrested, so we have 2. So it will be 3n minus 5. This I think you have studied, or maybe you will see it later. So that means if n is equal to 3, you have 3 into 3 minus 5, that is equivalent to 4. One of the one is actually shown as anti-symmetric. You have a symmetric stretch and you have 2 bending modes for carbon dioxide. These are the fundamental vibrations. Okay, I am just subtracting rotation. 2 rotation is subtracted, IP and IC. You remember we discussed that for a linear molecule. 3 translational degrees of freedom, which is common for any systems, you have to subtract it. Okay, so 1 atom of 3 coordinates, right? In the coordinate x, y, and z. So total you have 3, so 3 into 3, 9, minus 3 for translation and 2 for rotation for a linear molecule like carbon dioxide. So we have 4 fundamental vibration. I hope it is very clear. And then it goes on, then what I see is an anti-symmetric stretch, which is coming around 2200, 2400. This band is something around 2349 centimeter inverse, something around 2350 centimeter inverse. This we normally do in our lab. This is the corresponding bending mode. They are doubly degenerate. You see that the Q is allowed now because there are some selection rules which define it. Now delta J is equal to 0, which is the Q branch. This is the P branch. Here delta J is equal to -1. Here delta J is equal to +1. This is R. So this is some terminology they use. We call P branch, Q branch, and R branch. Q branch will be heavily populated. You see still a harmonicity playing a role. That's why it is slightly shifting. It will be the transition from the center point that you remember here. I was showing you transition 0 to 0. You'll see all of them up. I can represent this way. 0 to 0, then 1 to 1, 2 to 2, 3 to 3, etc. All this comes up. Okay, then that's why, and normally this appears when the vibration or oscillation happening perpendicular to the principal axis for linear molecules. Okay, and for carbon dioxide, this value is 4B. Okay, instead of 2b for linear molecule, it should be normally 2b. Okay, the gap between the spectrum, you remember as just before in the beginning I have shown it. But this is now 4b because it has a spin, nuclear spin come into picture. So selection will only allow even numbers. That is why this is coming as 4b. And so forth. So it goes on. So these slowly continue the same story. So this is one of the spectrum of R branch and P branch we have measured. You can see that in our spectrometer. This is one of the spectra that my student measured here in our lab. You see, it's not high resolution, still we can see it pretty clearly with 2 centimeter noise resolution. You can do it much better. You see that this is the Q branch, very clean Q branch of carbon dioxide molecule. Carbon dioxide is plenty abundant in the earth crust, right? I mean, you can see as a gas. It is roughly around 400 ppm, and people are now worried about carbon dioxide emission, carbon emission mainly. Okay, so Q branch, you see that the full width is 1 centimeter inverse. This is one of the gas which is mainly causing thermal, this due to industrial evolution. It has a very strong absorption ability, like water and carbon dioxide are the main component which is called as greenhouse gases. You know this. So that's why it's absorbed a lot of energy from atmosphere and heat up the atmosphere. Okay, so I will quickly move on to electronic spectroscopy. I now covered vibrational states, rotational states, and now I'll quickly give you a glimpse about electronic states. I will quickly go through. This is the small picture about an electronic transition. You see that in vibrations is another way of representing. That's why I'm saying you'll see many of these. This is your vibrational levels. And these are the electronic transition which normally come in the visible. If you have higher order, we call Rydberg state excitation that comes to UV. Or it can go to vacuum UV that happens below 200 nanometer. Okay, you can have some instrument even measure higher energy levels, higher order energy levels of molecules. Okay, so you see this is how it is. I'm skipping here to see an absorption event. I don't know whether they have shown this in the beginning. You can see an absorption which happened from ground to excited state. This process I said very fast in electronic level. I am just forgetting about all the vibration levels now. Absorption happened when the electronic wave function matches with the excited state electronic wave function. We call Frank quantum transitions. That when it reaches, you get maximum probability of excitation from here to here. This happened very fast. 10 at a second, which is roughly around 10 power minus 17 second. Right? Then it goes here, then you have vibration energies here available. Then it relaxes through the vibration energy, comes here, from there it falls to ground state. This is called fluorescence. You may be hearing this word, fluorescence. The fluorescence has many names, okay? Radiative decay, spontaneous emission, and so forth. Okay, so this process is a bit slower. You see that is happening in tens picosecond to a couple of nanoseconds sometimes, and it comes as fluorescence. And always fall from here in molecular system. This is called Kasha rule. So you have ground state electron distributions. And normally, this is Bryan-Kett notation to represent the ground state. And this is, that contains many wave functions together, include vibration, rotation, all the states together available here called as Bragi-Kett. The same way that I can write the wave function all together for the excited state E. This is a ground state. This is the excited state. So what happens here, you can define the transition as something called oscillator strength, which is connected to the transition dipole moment. That means if the population, population will be always here, right? And you get a probability. That's what Frank quantum state defines. And if that value is very high, you will have a better matching, so that you end up in having an interaction with the ground and the excited state in Q is a charge, R is a separation. So I will skip this term because you may be not able to quickly grab this. So, but you have to remember that each molecule, any time molecule you deal with, it has given absorption strength. Okay, that is also very important. For rotation and vibration and electronic state, you have given absorption strength. Okay, we call epsilon. This epsilon value will be normally measured in centimeter inverse, mole inverse, otherwise called as absorption cross section. Okay, absorption cross. I think in the first class I mentioned very briefly this, and that will tell you that in a cross section. Okay, if you take a cross section per molecule, the ability of the molecule to absorb energy. Okay, it will tell you that how much it can absorb light. Okay, so that comes from these transition probabilities. So this is called transition dipole moment. For electronic transition, they start from, say, for benzene, there will be roughly 20,000 centimeter inverse, mole inverse. For vibrational energy level, they will be very low values. They will be in the range of 100 to say maximum 1,000 centimeter inverse per mole inverse. Mole inverse. Rotations, I mean, I have not compared, maybe very, very less. You can check it. So the oscillator strength, the vibrations of electronic states is very strong, very high oscillator strength. Now you see how complicated a molecular state will be. You see, I can have all possibilities, absorption event, which is the green line, which is absorption excitation. It happens 10 power minus 15 to 10 power minus 17 second. Then it goes here, then you have many other internal conversion, inter-system crossing. Am I audible?
Yes.
Yes,
Yes, you are audible.
thank you. So then you have inter-system crossing, which is, you have internal conversion between the state, then inter-system crossing, which is shown by the blue line. As you can see here, then you have other level, which is a triplet state and so forth. So how complicated an energy landscape a molecule has. So many complex dynamic processes which can happen. So you start from rotation, vibration, and all the way up to electronic state. Now, so you simply take, so I have possibilities. I was just mentioning S0 to S2, S0 to S1, different possibilities. So you can have absorption, fluorescence, and phosphorescence event. This is another way of representing. Absorption can happen from S0 to S1 normally. This is also possible. If this is not possible, that means it's also followed by some symmetry rules. Okay. Then I have emission, which is from S1 to S0. Then triplet state emission is called phosphorescence. Absorption event happens very, very fast time scale. Vibration events happen this time scale. Okay, so you can see how the lifetime, how the system behaves. So this is for normally for electronic state transition. I'm just comparing vibrational relaxation here as well, because we studied just before for the vibration and energy levels. I go a little bit faster. I think we are already 4:30 now. So you take any compound, aromatic compound, benzene. You see here, benzene shows a beautiful absorption roughly around maximum around 254 nanometer, and it has some signature. You can see here, right? As I mentioned, I am just representing them, okay? As I mentioned previously, that the rotation can couple to vibration. Your vibration can couple to electronic state. So this is one of the reasons that benzene shows these fingers. Okay, it's very clear. You can have a transition, it's called Frank quantum transition, 0 to 0, 0 to 1, and 0 to 2, and so forth, that you normally see in benzene, which is given in some book. For example, I can give you a reference if you want to read about it, John Brooks. Okay, Photophysics of Polyaromatic Compound by John Brooks. This book may be available in the internet, or maybe you can see in your library. So this is an old book which explains how different kind of compound absorb, and it's beautifully written. This gap is one of the vibration of the benzene C double bond C stretching coming from the aromatic bond. And suppose you connect another benzene, that shift to even low energy, because there is actually, you may be doing this maybe in your BSc, how to see that the conjugation length increases from benzene to naphthalene to phenanthrene and anthracene and tetracene and pentacene and so forth. Is it tetracene when it comes, it's so beautifully been separated. You can see that. This will be the 0, 0, this will be the 1, 0, this will be the 2, 0, and so forth. I will show you that. This is a case of anthracene. Yeah, very clearly it is shown. I also have another book for you to read about it, due to our huge limitation of time. Photochemistry. There is a book written by Nicholas Turo. Okay, photochemistry, principles of photochemistry, photophysics, written by Nicholas Turo. They have explained it. So this part is your absorption event, this part, and this part is your emission. Okay, so you can have a possibility of transition from 0 to 0. It includes the vibrational state very clearly I was mentioning, then 0 to 1, 0 to 2, and so forth. Same way you can have, you will fall into S1. So this is not exactly correct. Kasha say that you have to come here. From there it will fall. Okay, that's most important. Okay, so some of the books is still wrong, so we have to check it. I just took it to explain it. Kasha rule says that you have to come through lowest vibration energy level to fall. Because it's always see the lowest energy level. It's like a continuum for the electronic state. From there it falls to the ground state. It still obey the Frank quantum rules. Okay, so there is no possibility of cross excitation from singlet to triplet state. It can only go through inter-system crossing, which basically some heavy atom involved, like spin get involved. This is another problem that again, maybe you will be interested later. So anthracene problems I have shown, and I think it goes on, like if I start talking about electronic state, is again complicated. Even in the case of benzene, I can explain you how liquid, solid, and gas phase benzene will look like. So you can see even rotational state coming in the benzene electronic spectrum when coupled to vibrational states. So there are some beautiful spectrum given by John Briggs in one of his book on polyaromatic compounds. So that's why you see rotational, vibrational, electronic states we covered, and I think this is the last part. I just thought of just telling you what I am doing in my lab. Okay, so
that would be great.
I was thinking about whether it was just too boring. That's just like to students, like sometimes they can think about it.
No, actually, what these topics, they are very familiar. Even overtone, vibration bands, overtones, even Fermi resonance, they know very basics. But you have explained it well, so it should be okay. They should be.
All right. Yeah. Okay. So, yeah, of course. I mean, if you have any questions, or if anybody have any questions, you please write me. I have no problem. I will definitely give as much as information possible from my side. So normally in our classes, when I take class here, students will, I mean, every 5 minutes I will have a question, so that will be very interactive. So what I am seeing now is it's like maybe that way that we will enjoy discussion wherever I go, but I know that is anyway, there are limitations in online courses. Of course, you being in online mode now, we are slowly evolving to learn how to live with it. So I don't know. So okay, no issue. So I will come back to what I am doing. Maybe I will show you 3-4 slides. Basics principle, what we are doing. So we are working on something called interaction of electromagnetic field, okay, light, which is heavily confined, and that get undergoing a reaction with the state. Interaction with the state, not reaction, interaction with the state. You have seen absorption event. Absorption event is actually you have light available. Light is exciting a system because the molecular state is available, right? So what happened here is that I am also confining the light in which I have one interaction, then the second interaction, and third interaction before it decay out. That's called strong coupling. So any kind of interaction between light and absorption is a weak interaction, I can say, that the molecule absorb, it leave. Okay, in our case, what we do is that when molecule absorb it give back the same light to photon and then take it back. It's like somebody is on the other side playing ping pong game. You may be like discus throw, whatever, that kids used to play, right? Ping pong, what you call table tennis, for example. A ball is moving from one side to the other side, coming back, going up, coming back. Okay, this is the game in which that creates some energy. This is very familiar to you, right? Molecules and zero-point energy. Students, I just explained you E is equal to, see, this time you forget, this is V plus half into H nu. Right? That means an atom or a molecule, so I can say molecule here, vibration comes only when bond is formed. So when a molecule vibrate, even your V, vibration quantum number is 0, you have possessing some energy because of uncertainty principle. That means it still vibrate. This is called zero-point energy. Okay? So that is quite fundamental, right? So I think about benzene molecule, I was just shown before. That electronic cloud is fluctuating, going up and going down. It's an oscillation. So everything is moving around us. So that's how even spontaneous emission occurs. I was thinking like spontaneous emission is nothing other than fluorescence. Fluorescence occurs when, okay, that is when more, you will feel complicated by thinking it, that we have space near to us, right? You're thinking that light is propagating with the speed C0, which is 3 into 10 power 10 centimeter per second. Why? This is the speed of light in vacuum, right? Vacuum has a meaning. This vacuum has a meaning which is the availability of infinite number of states. That means I have states like this, infinitely. Okay? If I match some of this energy, I can easily transfer this energy. This is my vacuum. So this is coming from the concept of quantum electrodynamics, where you define an infinite state available, which is vacuum. Vacuum is not nothing. Okay, it's just very clear. I am just, see, people are confused. It's a vacuum means that you take a ball and connect it to a rubber tube and pull. You think about take a metallic ball and just pull, and then you see that at very high vacuum the ball collapse, right? Or you fill a balloon, you fill some air into it. Opposite of what do you call nothing. The meaning of nothing is called vacuum in some way, right? But here nothing has something. Okay, which means that availability of infinite energy level. That is your half H nu comes in. That is the basic idea when Max Planck introduced this term, which is not correct classically, but it is correct quantum mechanically. Okay, so what I do is using this. I use this K, I make him like this, defined. Okay, I take this vacuum, which is infinity. I have all the states available in the vacuum. I make them defined by confining light. Then I will allow him to interact. So here it's a molecular state. So I am seeing, so you now see a double-headed arrow. Okay, so it's a molecule 1. This is molecule 2. These two are interacting. There is an exchange of photon occurring between this. So this is like the table tennis game. The ball is going from here to here, then coming back between two states. Okay, that create an interaction that split the energy into two. This will be something like minus d squared by r cube approximately, where d is the transition dipole moment, the absorbing strength of the molecule, and r is the distance separating these two transition dipoles. This create an upper level, we can call it as antibonding, equivalent to antibonding, and lower one which is equivalent to bonding. This is what in supramolecular chemistry, I don't know, some of you have heard about supramolecular chemistry, where aggregate forms, one molecule interact with another, so forth. They will have a common ground state, okay? Then I can have excitation possibility from here, as well as here. That will again defined by the selection rule. So in my lab, I'm not doing this, okay? In my lab, we replace this one of this molecular resonance by optical resonance. Okay, now I have a molecule here, I have optical component. This is called a cavity. So I take a cavity, I prepare a geometry, I confine those vacuum fluctuation, which I can call it as lambda y2 here. Okay, I have some defined value of it, which is nothing other than classically a standing wave of photon just trapped inside a cavity. Then this excited state, so what happens if energy is given? Then this state get excited, then it gives back. Given, gives back. Same ping pong game or table tennis here. So energy is being exchanged between the optical mode and the molecular state. You end up in having something like this. So I have given one photon, my ground state is going up here now, okay, in this case, and then this is emit, then same photon comes, excite, then it goes here, comes, repeat this process, 1, 2, 3, 4, how many cycles? Okay, this create an interaction. Okay, this is called Rabbi Oscillation. So when you create this interaction, you have a cavity plus an atom system, which is a new system, which has its own energy levels. Okay, this is what we are doing in our lab. So we create something called polaritonic states. These states are half molecule and half photon. So that's one. So it's not like the previous case, molecule mixed with molecule, you get same molecule or maybe another molecule, but here you create a photon coupled to a molecule to get something called polariton. So now we use this particular, so that interaction energies, etc., you forget about it, but you have an interaction which is nothing other than dipole into electric field here. Okay, electromagnetic field. That will give you a splitting energy as shown here. My original state was split into two, and this is called the polariton state or hybrid state. Okay, this is P plus and this is P minus. Now, the new system which is formed has very interesting properties. We can use it as, many chemical, physical studies. So my group is studying their spectroscopy, their chemical behavior. We are modifying chemical reaction by doing this. We are also studying electrical transport, something called polaritronics. These are the three major things that we are doing in our lab. So if you're interested, anyway, you can of course go to our website, and I'll be very happy if you want to interact with me at some point. So I have students. So Tabazum from Farooq College, he was a master student, but he has association with Farooq College before, and he left actually. He's in University of Southern California now. I have all others are, I have a student, Parvati is again another master student, she's from Kerala. She now is actually in Heidelberg University in Germany, started her PhD, and others, she is now in Delhi. And these are my PhD student. Jyoti is working on chemistry problem, we call it catalysis problem using field. Akila is working on spectroscopy here. Akila is working on spectroscopy. Jyoti is working on catalysis. Jayabir is also working on catalysis. Pooja is working on polaritronics, and she is also working on polaritronics. This is a postdoc. She is from IIT Kanpur. Now she's also working on some 2D material-based light matter process and its interactions. This is my small group. So if anybody is interested, you can contact me related to academic or research-oriented steps. Thank you. I will be happy to get your feedback, if any.
Yes, students, if you have any particular questions on this topic, please feel to ask him directly. I don't know whether most of your students are there from physics background or chemistry background exactly. Masters in chemistry or interdisciplinary?
So actually, I was telling you that we are working on interdisciplinary problem that half of my students are from physics and half of them are from chemistry. Being in IISER Mohali, we have that freedom. I mean,
Yeah, that's good.
so we have students across the department.
So when you offer the PhD, which subject do you give them? I mean,
It depends. I mean, suppose their master degree is in chemistry, they will be offered degree in chemistry.
okay.
It is also possible to do a degree in physics, but then you should basically have to pass through all the comprehensive and other tests. So there is no written rule like that.
Okay.
But okay, so that is not a problem. Like if you are more comfortable in doing after your master's in physics, then you can of course join in the physics department.
Yeah, that is the need of the hour because everyone is encouraging for the interdisciplinary research rather than specifying onto the subjects.
Yes, yeah.
Yeah, true. Now, for the last part of the research part which you have mentioned, what are the types of molecules you use? Organic molecules or inorganic type of complexes? What do you
use? Jyoti was doing one experiment. Here again we call vibrational strong coupling. We take a simple ester.
Okay.
Can call as para-nitrophenyl acetate. This molecule, that's a classical molecule we tried. There has a carbonyl group. We couple them to the field, infrared photon, and we could catalyze them by coupling it very precisely by doing it. So we are now actually, I mean, that's the first thing that we showed from here. That's called cavity catalysis. That's actually first experimental proof that we could change the rate of the chemical conversion by coupling to a vacuum fluctuation. So here we are not giving, it's not conventional, okay? So we are not giving photon from outside. The geometry is defining it due to vacuum fluctuation, it is created. So I just need to inject the reacting solution into a cell which contains cavity.
That's interesting.
So this is called polariton chemistry.
Okay.
There are more details given in the textbook.
Yeah, of course.
Sorry, in the website.
Website also maybe.
Please, you will be able to see more details definitely, I mean, including publication and other things.
Yes, students should take this. Yeah, students should use this opportunity because when they are given for assignment and seminars, they should come up and write such things. And also when they write for some summer research fellowships, should not be always looking for the very traditional classic catalysis. These are some new topics and catchwords where they should definitely look upon and write. For that, you will high chance of getting your summer research fellowships also. That's what we always encourage. Catch these new concepts. There are students, more funds are given. So this is exactly really useful things. Yes. Dr. Tanya, please.
Yeah, it is great listening to Dr. Jino George for the past 3 days. We had a flare of the basic spectroscopy and the interaction with matter on the first day, followed by a rotational spectroscopy, and almost the whole principle of rotational spectroscopy along with the applications was covered. And today we had a talk on vibrational electronic and finally what actually Jino is doing at present. So that actually transformed the talk. We could see the passion of what you've been doing in research from your talk, and had an idea about the Rabbi oscillations as well as a new concept of polaritons.
Yeah.
So hope the students will check up what this polaritons is, and they will also pursue that in their research. Thank you so much, Dr. Jino, on behalf of Department of Chemistry, St. Joseph's College, Devagiri, as well as IISER. And hope we have more collaborations in future as student exchange or faculty. If you can come over to Devagiri anytime, you're most welcome to have personal interaction with the students.
Sure.
Thank you so much. Thank you so much, Professor Jino.
Thank you. I have also one word to say to the students that what I've taught in 3 days is normally given as a semester problem for you.
That's
So you should not get afraid or get bored to what I have been. So one more thing, that if you come to research part, that is the most enjoyable part, because once you learn the fundamental, of course, that's basically sometimes very boring. But I know that being a student, when I was BSc or MSc student, I was bored to study spectroscopy as it is. This is what my feeling is. I just want to tell you. But once you come into a lab and start doing yourself and seeing this happening, I was saying many times seeing a spectra beautiful because this is how it looked like. It explained the entire system. So if you come to lab and see it, you will see it different. Your mindset itself will change. And second thing, that I know that there is a pandemic going on around and so forth. So I request students to come out. Actually, I mean, seeing in North India, at least students are asking questions. So you should come out of this and ask questions. Otherwise, it will be very difficult for you to survive in future, because if you will have to have your own questions ready and ask. Okay, this is how you see. If you go outside, you will see any places. That's the only way to learn. Okay, that's the only way to learn anything, or you have to otherwise teach. Okay, so either teach or ask questions. These are the only ways. I encourage students to do it, and please do that. That basically make your way to success. Okay, all the best. I'm very happy that being a couple of days here and interacting with many of you. Hope it has been transformed some of your thoughts. Maybe, I don't know. Like at least you get some glimpse about spectroscopy. You're most welcome to IISER Mohali at any point of time to interact with me and my friends here. Okay, thank you very much, and we will keep in touch.
Yes. Yeah, thank you very much, Dr. Jino, because this was good, because you can see how an expert connects the IR, UV, I mean, the rotational spectra, how that smooth transition with all these equations. So it was wonderful to see. At least the teachers will definitely benefit more than the students at this stage, because we are all listening to your talk. So we are very happy and taking out this time in spite of your very, very busy schedule. We appreciate that for your valuable time spending on us. So thank you very much.
Thank you.
Yeah. Hope you meet
Have
you.
a nice time. Thank you.
Yeah, I am also conveying to the regards of Jomon. As
sure.
You know, he could not attend the last session, but
hope he is doing well. And
yeah, he's
fine.
Yeah. So that's thank you very
Bye.
much.
Bye.
And all the participants, please fill in the feedback form I have shared with you, and we will have the next sessions from Tuesday. That's on coordination chemistry by Dr. Ajay Venugopal from IISER Trivandrum. I request you all to join. We will inform you in the group. Thank you all. Thank you all. Thank you all students and the faculty members who attended this talk. Thank you.